that is maybe not very easily evaluated using a polynomial, because polynomials are the easiest types of functions to evaluate. And then we went on and said, okay, well, we get this new kind of polynomial. Well, what would happen if we took those polynomials out infinitely many term? Instead of having a fourth degree polynomial approximation, we would have what we would consider an infinite degree polynomial approximation. And specifically, we looked at various types of those series in the last section, and they're called power series. So kind of in this next section or two, what we're going to try to do is bring those two together. Okay, so we know how to approximate a function using a polynomial approximation, or if we have an infinite power series, we know how to find x values for which they converge. So in section 11.3, what we're going to talk about is how do we find power series representations for particular functions. They gave us a few in the last section. Said a power series representation for f of x equals 1 over 1 minus x equals blank, and so on and so forth. But how did they come up with that? Well, it's pretty simple if you want to know the truth. We're just going to expand the idea of those Taylor polynomials that we found in section 11.1 out to infinitely many terms. So specifically, if you have a function that has derivatives of all orders, in other words, it's infinitely differentiable, okay, at a point on an interval centered at the point A. So like if we're centering it at 0, we can go, a little bit to the right and a little bit to the left at least, and still have an infinitely differentiable function. Then what we say the Taylor series for that function is centered at A. It's just the Taylor polynomial infinitely long. Okay, so rather than taking the summation from k equals 0 to n, where we stop at 4 or 5 or whatever, we're going to take the Taylor polynomial out to infinitely many terms. So these coefficients that we have here in the Taylor series, the f of k, the kth derivative of f evaluated at a, should be like that, over k factorial times x minus a to the k. These guys are the same coefficients that we found when we were doing Taylor polynomials in section 11.1. Now, if a is 0, we do call it a Maclaurin series. Okay, but so if they say Maclaurin series, it's automatically centered at 0. And a lot of times they won't specify if they say Maclaurin series. Okay, but two things we need to know. For what values do those series of this type converge? And, okay, just because they converge, do they actually converge to the given function for all x values? And for us, most of the time, that answer will be a yes. But to be honest with you, the answering of that question is a bit more involved. We'll talk a little bit about it, but actually not a whole lot. All right, so let's just kind of review. If I gave you the function f of x equals the natural log of 1 plus x, and I ask you to find the power series using summation notation and determine the interval of convergence of the series. Usually what I'm going to try to do is I'm going to find the first few terms of the Maclaurin series, just like we did in section 11.1. This time they specifically asked us to find 4 terms. In general, how many terms do you need to find before you can put it in summation notation? It just depends. The more complicated the function, the more terms you may need to write down to be able to see the pattern. But let's just start and find the first 4 non-zero terms of the Maclaurin series. So our first step is to write down our function. And if we're going to have to find the first 4 non-zero terms, I know I'm going to have to take at least a 3rd degree polynomial. So I'm going to go ahead and take at least the first 3 derivatives. And I may need more, and we'll check here in just a second. The first derivative of this would be 1 over 1 plus x, or 1 plus x to the negative 1. The second derivative would be negative 1 times 1 plus x to the negative 2. The third derivative would be negative 2 times negative 1 is 2 times 1 plus x to the negative 3. So if we plug in our center, which is 0 because it says Maclaurin series, I'd have the natural log of 1 plus 0, which is the natural log of 1, which is 0. Immediately I know I'm going to have to find another derivative. Why? Because they asked for the first 4 non-zero terms. Instead of saying they wanted the third degree polynomial or the fourth degree polynomial, they want us to take derivatives out until I find 4 coefficients that aren't 0. Okay? I'm going to go ahead and finish plugging these in, and then we'll figure out how many more derivatives we need to take. If I plug in x equals 0 here, I have 1 over 1 plus 0, which is 1. If I plug in 0 here, I'll have negative 1 over 1, which is negative 1. And if I plug in 0 here, I will have 2. So at this point, I have enough derivatives taken that I will find 3 non-zero terms. Since I want 4, I'm going to go ahead and take one more derivative. Using the chain rule there, we just get negative 6 times 1 plus x to the negative 4. If you plug in a equals 0, we just have negative 6. So the first 4 non-zero terms are, well, I usually typically write them out as I would if I was going to put the polynomial. Here I would have had f of 0 over 0 factorial, f prime of 0 over 1 factorial times x minus 0, f double prime of 0 over 2 factorial times x minus 0 squared, f triple prime of 0 over 3 factorial times x minus 0 cubed, and then the fourth one, since we had to find it, will be the fourth derivative at 0 over 4 factorial times x minus 0 to the fourth. This one, since this term is 0, that one's 0. Okay. Now, if I was finding my fourth degree Taylor polynomial, I would have pluses between these. Right? But I just want to list out the terms here. So my first non-zero term will be 1 over 1 factorial times x, which is just x. The second non-zero term will be negative 1 over 2 factorial times x squared. The third will be positive 2 over 3 factorial times x cubed. And the fourth is negative 6 over 4 factorial times x to the fourth. Okay, so when they ask you in my math lab, they typically just ask you to list the terms. They'll say, you know, what's the first non-zero term of that, the second, third, and fourth. So this would be our first non-zero term, second non-zero term, third, etc. Okay. So first 4 non-zero terms are x, negative 1/2 x squared, 2 over 3 factorial is 1/3 x cubed, 6 over 4 factorial. 4 factorial is 24, so 6 over 24 would be 1/4. So that would be negative 1/4 x to the fourth. Those would be the first 4 non-zero terms. Now, before we go on, is everybody okay with that part? All right, so then we also want to write the power series using summation notation. So if we looked at our Taylor polynomial, or in this case Maclaurin polynomial, we would have had x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the fourth, and so on and so forth. Okay, what we want to do is rewrite that in summation notation. So I'll take the summation from k equals, now it just depends, we can start this at 0 or we can start it at 1. It's going to depend on what you want to do. Now sometimes they'll specify where they want you to start it, sometimes they won't, but for the most part I think they usually start them at 0 or 1. I mean, you know, typically. I'm going to start this one at 1 to go along with the fact that I have a first x to the first as my first term, right? So I'm going to go from 1 to infinity. The alternating part I'm going to write as -1 to either the k plus 1 or the k minus 1. Why couldn't I just use -1 to the k? Well, if my first term starts at k equals 1, if I just use -1 to the k, that would give me my first term is negative. But it's not. It's positive. So I'm going to use -1 to the k plus 1. My numerators of my coefficients are all size 1. And then my exponents go x to the first, x to the second, third, fourth. So I'm just going to say it's going to be x to the k over the denominators are 1, 2, 3, 4, etc. So it'll just be x to the k over k. Questions? Well, look at the denominators here. This is like x over 1. This is over 2, over 3, over 4. My counter starts at k equals 1, so it just goes 1, 2, 3, 4, or my denominator is just the counter. Okay. Now, this would be the power series using summation notation. Okay. They also want us to determine the interval of convergence. So we're going to take that power series. I'm just going to write it down and then I'll move this up. Hang on just one second. I want to find the interval of convergence for this power series. So we can go back to what we did in the last section and use either the ratio or the root test. I'm going to use the root test, and we'd be looking at the limit as k approaches infinity of the kth root of the absolute value of -1 to the k plus 1. Oh, x to the k over k. Now, -1 to the k plus 1 times to the 1 over k. Guys, that's really just going to be -1 to this k to the k plus 1, or 1 over k to the k plus 1. Multiply the exponents, you're going to get 1 plus 1 over k. And so what's really happening there is when you take the absolute value of that -1 to the power, you're going to end up with a positive 1. Yeah. And then we take the kth root of the absolute value of x to the k, and we'll get the limit as k approaches infinity of the absolute value of x times, or over, depending on how you want to write it, the kth root of k. Now notice I didn't put the absolute value around that k in the bottom simply because the k's are going to positive infinity, so they are positive. Now we talked about this guy a couple times, I think it was last week. That limit is just 1, so we end up with the absolute value of x over 1. If you don't remember that limit is 1, you'd have to go back and use L'Hopital's rule on the corresponding function. So we know by the root test, and we would have gotten the same thing by the ratio test, but by the root test, this series converges when that limit is less than 1, which is -1 is less than x is less than 1. It diverges when that limit is bigger than 1, and we don't know what happens when that limit actually equals 1. So since we use the root test, we would have to check the endpoints separately. Okay? So when we plug in x equals -1 and x equals +1, okay, if I replace the x with -1, I'll have the summation from k equals 1 to infinity of -1 to the k plus 1 times -1 to the k all over k. And if I plug in x equals +1, I will have the summation from k equals 1 to infinity of -1 to the k plus 1 times 1 to the k over k. 1 to the k is always 1. So here we have, did I just plug that in right? Let me look. Yeah, okay. And here we have what? This would be -1 to the k plus 1 plus k is 2k plus 1 over k. Is everybody all right so far? What kind of number is 2k plus 1 always going to be? Even or odd? Odd. -1 to any odd power is always -1. So this is -1 over k. And this is -1 to the k plus 1 over k. So this is the alternating harmonic series. The limit as k approaches infinity of the 1 over k equals 0, and 1 over k plus 1 is less than 1 over k. So by both of these things, this series converges by the alternating series test. This is just the negative of the harmonic series, so that is a divergent p-series. So for this particular series, we converge for all the x's between -1 and 1. We converge at x equals +1, and we diverge at x equals -1. So the interval of convergence here would be from -1 to +1, excluding -1 and including +1. So we could also say it converges for -1 less than x, and x is less than or equal to +1. But you know, they gave us that particular series in the last section, but they didn't really tell us where it came from, right? They just told us in one of our homework problems in the text, and we did a couple with it, that was the power series representation for the natural log of 1 plus x, and that was the interval of convergence. And we've just shown that to be true. A lot of times the big challenge in these is recognizing the pattern that's going on, you know, taking enough terms finding enough non-zero terms that you can recognize a pattern so that you can write it in summation notation. Questions before we go on? All right, well, let's try another one. You remember, we don't always have to center at 0, right? We like it when they're centered at 0, but that's not always possible. And sometimes we just don't, for various reasons. So let's suppose we have sine x, and we want to center at x equals pi over 4. Okay, so let's first thing, we're going to find the first three non-zero terms of the power series. To find three non-zero terms, we're going to have to take at least two derivatives. And we can stop there if that's all, none of them are zero. So I'm going to start out with my function. My first derivative will be cosine x, and my second derivative will be negative sine x. Then I'm going to evaluate those functions at the center and hope that none of them are zero. If I plug in x equals pi over 4 here, I get the sine of pi over 4, which is square root of 2 over 2. Cosine of pi over 4 is also the square root of 2 over 2. Negative sine of pi over 4 is negative square root of 2 over 2. Okay. Now, this one's a little bit odd in that we didn't go plus minus, we went plus plus minus. What would the next one be? Just in the interest of, we're about to have to write it in summation notation. If we had wanted another one, that next one would have been a negative sign as well, wouldn't it? Because the derivative of sine x is cosine x, so it keeps the same plus or minus sign. So we'd have f triple prime of pi over 4 would be negative square root of 2 over 2 again. So rather than doing a true kind of alternating every other term, it's doing alternating every two terms. Okay, but that's neither here nor there yet. The first three non-zero terms, we would have f of 0 over 0 factorial, f prime, not 0, pi over 4, f of pi over 4 over 0 factorial, f prime of pi over 4 over 1 factorial times x minus pi over 4, f double prime of pi over 4 over 2 factorial times x minus pi over 4 squared. And those would be the first three non-zero terms of the power series. F of pi over 4 was square root of 2 over 2 over 1. So I've just got square root of 2 over 2. That would be the first non-zero term. Here, f prime of pi over 4 would be square root of 2 over 1 times x minus pi over 4. F double prime will be negative square root of 2 over 2 factorial times x minus pi over 4 squared. That would be the first non-zero term, the second non-zero term, and the third non-zero term. Now, is everybody okay so far? All right, so what would be our fourth non-zero term? Well, it would be negative square root of 2 over 3 factorial times x minus pi over 4 squared. Oh, not squared, cubed, sorry. And it just keep going and going. So notice that the numerator in each one of these has a square root of 2 over 2 for it. So if you wrote down the polynomial that went with this, we would have square root of 2 over 2 plus the square root of 2 over 2 times x minus pi over 4 minus the square root of 2 over 2 factorial. Now technically you could write this as a 1 factorial in the bottom and a 0 factorial in the bottom if you wanted to, because remember 0 and 1 factorial are both 1. So we have that times x minus pi over 4 squared minus square root of 2 over 2 times x minus pi over 4 to the third. Can anybody tell me what that next term would be without writing it down, just recognizing the pattern? What are we going to have? Does help when you write the whole thing down. Yeah, I think you said it just fine. Times x minus pi over 4 to the fourth, and so on and so forth. So we can definitely see the pattern, right? We go 2 positives, 2 negatives, 2 positives, 2 negatives, and so on and so forth. The problem is how to write that in summation notation. One thing that we could do, we could factor the square root of 2 over 2 out front, right? So I'm just going to take the square root of 2 over 2 that's in every single one of these terms and pull it out front. And so then I would have, let's see, 1 plus x minus pi over 4 over 1 factorial. So this would be a 1 over 0 factorial, x minus pi over 4 over 1 factorial, minus x minus pi over 4 squared over 2 factorial, minus x minus pi over 4 cubed over 3 factorial, and I'm just going to do one more just for fun. Then we'd have a minus, or no, another plus, and so on and so forth. Okay. How in the world can we get those 2 pluses, then 2 minuses, then 2 pluses, then 2 minuses? Sometimes, now this won't be common, guys, but if you wanted to write this in summation notation, one thing that you could do is break it in half. So since we're adding these together, does it matter in what order you add things? No, a plus b plus c is the same thing as c plus a plus b. You know, their addition is commutative. It doesn't matter the order in which you do it. And so what I'm going to do is I'm going to rewrite the orders. So I'm going to take this term, this term, this term, in other words, the even powers, and I'm going to group them together. And I'm going to also group the odd powers together. So I'm going to also group this one, now, why might that help me? If I look at my even terms, notice every other one of them is positive, every other one's negative. And the same is true for my odd terms. So I would have the square root of 2 over 2 out here in front times. Let's write a formula for the even powers only right now. I'm going to take the summation from k equals 0 to infinity of, I need x minus pi over 4 to the, here it was to the 0 power, here it's to the 2nd power, here it's to the 4th power. In other words, I'm going to put the 2k power up there, over, the denominators are 0 factorial, 2 factorial, 4 factorial, or in other words, the power and the factorial are the same. So I'm going to have 2k factorial. How am I going to get the -1 alternating? First one's positive, second one's negative, third one's positive, so I'm just going to put a -1 to the k there. Now, does that give me all my terms? No, that only gives me my even powers. So now, let's do something similar for the odd powers. And I'll have plus for the ones in green, summation from, let's see, do we want to, let's just start it at 0 since we started the other one at 0. Okay. I want the first one to be positive, the second one to be negative, third one to be positive. So once again, since I'm starting at 0, I'm going to call this negative 1 to the k. And the powers to which x minus pi over 4 is raised would be x minus pi over 4 to the first, third, fifth. So that'll be a 2k plus 1 over 2k plus 1 factorial. Now, this one I probably should have waited till a little bit later to do this example, simply because the fact that it goes plus plus minus minus plus plus is not a very common thing for what we'll be doing. But if that happens, you can break it apart and make it into 2 summations. Okay? Or you could, I mean, technically you could have 2 or 3 or 4 summations. We just won't have any that we have to go that far for as far as our homework is concerned. Okay? Questions? On your test on Monday, I am really toying with the fact that you may not be able to enter your answers in My Math Lab at all. Would that be okay with you guys? And it's really just to save you some time, because typing stuff like this in takes a lot of time. Okay, so I think what we'll do on Monday on your test is, you'll go into My Math Lab just like normal, and open your test, but the questions won't have blanks for you to enter your answers. And like I said, a lot of it's just because this can be really, really time consuming. And so I'll just ask that you show it all on your supporting work paper. .4, yeah. Now I think there was a section or two. Well, no, we did 10.1 through 10.8, and then 11.1 through 4. Now, 10.8, though, wasn't anything different. It was just, some practice on a variety of series tests. All right. So I want you guys to try one. I want you to use the definition, which is what we've been doing, okay, to find the Maclaurin series for f of x equals e to the x, okay? So the first thing I want you to do is write out the first 3 non-zero terms of the Maclaurin series, and then see if you can put it in summation notation, and then we'll talk about the interval of convergence in a minute. But I just want to give you a few minutes to work on those first 3 non-zero terms. Are you ready to look at the first three terms? Okay, what's the first derivative? Gosh, we love e to the x, don't we? And the second derivative, same. So when we plug in a equals 0, we would get 1, 1, and 1. Yes? So if we were trying to write out the first few terms of this Maclaurin series, we would have 1 over 0 factorial plus 1 over 1 factorial times x minus 0 to the first plus 1 over 2 factorial times x minus 0 to the second. This, and this would be the first three terms, or the first three non-zero terms of the Maclaurin series. So we have 1 plus x over 1 factorial plus x squared over 2 factorial. Now remember, technically this was over 0 factorial. So could you guess what that third one would be? Perfect. And then we'd go x to the fourth over 4 factorial and so on and so forth. So we recognize the pattern, and our series, we could start it from k equals 0 to infinity of x to the k, x to the 0, x to the first, second, third, and fourth, over k factorial. This is the Maclaurin series for e to the x. And if we did the ratio test to find the interval of convergence, we'd be looking at the limit as k approaches infinity of the absolute value of x to the k plus 1 over k plus 1 factorial times k factorial over x to the k. That cancels with that and leaves an x, which I'm going to bring out front. The limit as k approaches infinity of k factorial cancels with k plus 1 factorial and leaves a 1 over k plus 1. This guy goes to 0, so that means the limit that we get is equal to 0, which is always less than 1, and our interval of convergence would be all real numbers or from negative infinity to positive infinity. Any questions about the process? All right. Go ahead and take about a 5-minute break. It's 1:03 according to my clock, and so we'll start back up at 1:08. All right. So what's really, we've discussed this before, but one of the things that's so cool about power series is when you take the composition of a function and another function, as long as what you're plugging in for x to replace x with in the power series is in the interval of convergence, we don't have to start over to find a power series. We can use ones that we've already developed. So, I mean, could we take f of x equals e to the 3x and just kind of brute force take the first three derivatives of it and find a power series representation for it? Sure, we could. But we could also use the fact that, okay, we just derived the fact that e to the x as a power series is represented by k equals 0 to infinity of x to the k over k factorial. So if I wanted to find a power series representation for e to the 3x, rather than starting over, I'm just going to use the fact that that is f of 3x, where f of x is e to the x. So I'm going to call this g, sorry. Okay. So a power series representation for that would be the summation from k equals 0 to infinity of 3x to the k over k factorial. Easy peasy, and we're done. And it won't change the interval of convergence. So what would it be if we took x squared times e to the x? Well, let's call this one h. If we wanted to find a power series representation for x squared e to the x, that would just be x squared times the summation from k equals 0 to infinity of x to the k over k factorial, which is the summation from k equals 0 to infinity of x squared times x to the k over k factorial. And remember, when you take x squared times x to the k, that's x to the 2 plus k. So we would have a power series representation of k equals 0 to infinity of x to the 2 plus k over k factorial. And notice, if we were doing that one kind of with brute force, going through and finding the derivatives and things like that, we're going to have to go through several derivatives because when we take the derivative of this function, we'd have to use the product rule. And so we may have some terms that are zeros or whatever. But it saves us a huge amount of time to just be able to use the composition of functions involving the power series. Okay. Questions so far? All right, just so that I don't forget to do it later, if you're still here with me, would you type here? Thank you. All right, so let's look at an example here. It says differentiate the Maclaurin series for the function f of x equals e to the negative 8x. Identify the function represented by that power series, give the interval of convergence, and so on and so forth. Okay, so let's look at a power series for e to the 8x, or negative 8x, sorry. We know what a power series representation is for the function e to the x, and we just talked about how we could use that to find a power series representation for e to some other function, right? So let's first think about the fact that if e to the x is written as a power series, we write it as summation from k equals 0 to infinity of x to the k over k factorial. Furthermore, we know that the interval of convergence is from negative infinity to positive infinity. Okay? Now, if we use that to find a power series representation for e to the negative 8x, really got to quit calling these the same number or same letter. So we're going to use a power series representation for e to the negative 8x. That would be the summation from k equals 0 to infinity of negative 8x to the k over k factorial. Now that part we've done before, right? Is everybody okay with that part so far? So specifically what we would have is when k is equal to 0, this would be 1 over 0 factorial. When k is equal to 1, we would have negative 8x to the first is minus 8x over 1 factorial. When k is equal to 2, we'll have 64x squared over 2 factorial minus, what's 8 to the third? 64 times 8. 512x to the third over 3 factorial, and so on and so forth. That's what that series would look like. So if we take the derivative of this power series, we'll be taking the derivative of, I'm going to sneeze, I'm so sorry. Oh, okay. We'll be taking the derivative of 1 over 0 factorial minus all this good stuff. I should have just left myself more room up. Line above. The derivative of this term would be 0. The derivative of this term, now remember these denominators are just constants, so they're just kind of hang out down there. Derivative of 8x is negative 8 over 1 factorial, plus we have 64 times 2 is 128 over 2 factorial, minus 3 times 512 would be what, 1536? And so on and so forth. Okay, so I'm kind of doing this one brute force so far. Oh, I'm sorry, 128x. Yes, thank you. Okay. So let's see. What do I expect my derivative to be? Well, I expect my derivative to be the same as the derivative of e to the negative 8x, just in an exponential, or not exponential, but in power series form. So I'm going to see if I can figure out how to rewrite that. Okay, if I took the derivative of e to the negative 8x, I would have e to the negative 8x times what? Negative 8, right? Because of the derivative of the exponent. Can I factor a negative 8 out of these terms? Well, it looks like it. That would be a negative 8 times, let's see, 1 over 1 factorial. If I factor a negative 8 out there, 128 divided by negative 8 is what? Oops. 16. Yeah, thank you. Let's see. So I've got, let's see. All right. 1536 divided by negative 8. Oops, plus. And so on and so forth. Okay. And you go, okay, well, what's going on there? First of all, I'm going to double check my arithmetic before we go any further because, yeah, that sometimes gets me in trouble. Okay. Okay, I think I've got the arithmetic all good. Okay, so how are we going to rewrite this? Well, if you look at each one of these, keep in mind what we're trying to think of is, can I get something times, what I'm expecting is a negative 8 times this power series. right? Because this was the original power series for e to the negative 8x. So when I take the derivative, if everything works out as it should, I should get negative 8 times this power series. So I've got this, okay? And then the question becomes, do I have these terms up there somewhere? Well, if you think about negative 16x, that would be negative 8 times, let's see, this would be just a 1 over 1 factorial. 16 is negative 8x times 2. 2 over 2 factorial. If I take this guy, I would have 8x cubed. No, 8x squared, sorry. Times 3 over 3 factorial. Because 192 divided by 64 is 3. That's where I'm getting that. Why am I doing that again? Remember, I'm trying to figure out if I've got these terms up here. The next one we would have a negative 8. No. Because no. I have negative 8x squared, which is 64x squared. Yeah, okay. The next term, we'd have negative 8x to the cubed, or to the third, times 4 over 4 factorial, and so on and so forth. And we're doing this one by brute force. I mean, we actually just wrote out the terms of the series and we're taking the derivative term by term. But that would be, excuse me, the same thing as, okay, this is just 1, right? Okay. This is negative 8x. This 2 will cancel with that and leave a 1 factorial. This 3 will cancel with that. 3 over 3 factorial is 2 factorial. 4 over 4 factorial is 3 factorial. So we end up with minus or plus a negative 8x over 1 factorial plus a negative 8x squared over 2 factorial plus a negative 8x cubed over 3 factorial, and so on and so forth. Now remember, this 1, you can write it in a variety of ways. Specifically, we could write it as 1 over 0 factorial or negative 8x to the 0 over 0 factorial. And we would get negative 8 times the summation from k equals 0 to infinity of negative 8x to the k over k factorial, just in summation notation. So we have negative 8 times this power series, which is negative 8 e to the negative 8x. So we got, and we were able to show that just by going through and taking the derivative term by term, that the derivative we got really was negative 8 times the power series for e to the negative 8x. Now, that's the brute force method. I mean, like I said, we literally just wrote down the terms and we took the derivative term by term. If we had gone back up to our original power series and you said, oh, well, if e to the negative 8x is the summation from k equals 0 of negative 8x to the k over k factorial, how do you take the derivative of that inside the summation notation? Because this, I mean, you got to admit, this is kind of a long drawn out process when you have to take the derivative term by term and do all the factorization. When you have 8x to the k, if you take the derivative of that, all right, what would we get? Well, we'll have a summation of the k factorial's just hanging out down there because it's just a constant for each k. The derivative of negative 8x to the k would be k times negative 8x to the k minus 1 times the derivative of negative 8x, which is negative 8. Okay. Is everybody okay with that part so far? All right. Now, simplifying, that's going to be a negative 8. Cancel with that, k minus 1. Because remember, k cancels with k factorial and leaves a k minus 1 factorial. So we will have negative 8 times negative 8x to the k minus 1 over k minus 1 factorial. Now, this is what we were talking about the other day, right before we left. When you take the derivative term by term, sometimes, though this one started at k equals 0, when we move and take that derivative, this one actually starts at k equals 1. Because if you go back and look at the terms that we had when we took the derivative, our first term would actually end up being just a 1 in our, well, not that y'all can see that, sorry. Okay, our first term here ended up being a 1 times a negative 8. If we started that at 0, or pardon me, if we started at 1, we'll have negative 8x to the first minus, or to the 1 minus 1, which is 0. So that becomes our negative 8 times 1 there when we started at k equals 1. So you do have to be careful a little bit that you move your starting k value accordingly. But that would also give us the summation that we got earlier starting at a different spot. Not always, because see, I can rewrite this one starting at 0 if I wanted to. The way this one looks here, it would start at 1 to match up with the terms that we had initially. But if I wanted to shift it to starting at 0, okay, that negative 8 is just hanging out there. I mean, it just is multiplied. But if I shift this to the left 1, that means I'm going to replace my k's with k plus 1. So I'd have k plus 1 minus 1 would be negative 8x to the k over k factorial. So I can shift it back to starting at 0. But in this particular case, when I took the derivatives term by term, I would have had to shift it initially over to starting at 1. You just have to pay attention to those first couple of terms to make sure that whatever your starting k value is would actually give you the first term of your series after you took the derivative. I mean, I could start at k equals 1, k equals 0, or k equals 27 if we really wanted to. We just typically started at one of those two places if possible. Just remember though, when you're shifting, you're really just doing a horizontal shift of a function, just like you did in college algebra. When you replace k with k plus 1, that shifts everything left 1 unit for k. When you replace k equals 1 with k equals 0, that was a shift left, right? If we wanted to shift it right, you replace k with k minus 1 throughout the entire series. But either way we go, whether we took the derivative term by term brute force, or we took the derivative using the summation notation, we still got negative 8 times the summation from k equals 0 to infinity of negative 8x to the k over k factorial, which is e to the negative 8x. So we got negative 8 e to the negative 8x. Whether we did it via the summation notation version or just the writing them all out and taking the derivative term by term. Now, with the interval of convergence, when you're taking the derivative, when you take the derivative of a power series, your interval of convergence won't change except possibly at the endpoints. So like if we had an original interval of convergence from negative 1 to 1, you would need to check the convergence at those endpoints. But since the original interval of convergence for e to the x, or e to the negative 8x, was already negative infinity to positive infinity, this one will also have that interval. Okay, so it's only if you have endpoints that you're going to have to check and be careful. Well, when you say e to the whatever, you got to be a little bit more specific. Like if you have like e to the x or e to the 3x or e to the 5x, then yes. Something like that. Yeah. All right. So I was going to look and see if I could find another one. Yes, because multiplying by that x, you're just multiplying by an x that's inside the original interval of convergence, so you're not going to change it. E to the x really is our most well-behaved function, particularly for power series, because it just doesn't, when you're doing a Maclaurin series or whatever, and you can take the derivative however many times you want and get the same thing every single time, it's just really nice. Because it just makes everything work really well. Now notice, guys, how many of you actually have a hard copy of the text? It doesn't matter if you do or not. You have a copy of the textbook inside your multimedia library. So even if you don't have a hard copy of the text, you have this page inside the multimedia library. Notice on page 740, they've given you a list or a table of some of our more common power series representations. Now, just to be honest with you, I told you, two of the questions that we needed to ask were, for what x values do the series converge? And do they always converge to the function in question? And for some really wild functions out there, they may not always converge to the original function. For some kind of maniacal series. For all of these, they not only converge on the interval that they tell you they converge, they also converge to the given function on that interval. To determine whether a function converges to, or whether a series converges to the given function, involves looking at the remainder theorem, which was talked about in section 11.1. They tell us kind of, a function is equal to its polynomial approximation plus what we call the remainder. And if you can show that that remainder is approaching 0, then that means the series converges to the original function for all of the x's in the interval of convergence. Sometimes showing that particular thing can be a bit tricky. And the ones that we're doing are going to be well behaved as far as they are going to converge to the function under consideration. But just be aware that for some more, difficult types of functions, you could possibly come up with a power series that for some of the x values in its interval of convergence, the series didn't converge to the original function itself. Okay, we're not going to spend really much time talking about that part, but it is a possibility. I'd rather instead look at another example of kind of what we were just doing here to make sure that you've got the process down okay. So let's look at, oh, and by the way, this table, you don't have to memorize this by any means. I'm not asking you to do that. It is kind of good if you have, e to the x, sine x, cosine x, those kind of, at least familiar in your head, because that way it's a lot easier for you to check yourselves. On your test, what I will typically ask you to do is use the definition to find a power series representation for a function. So you would actually be deriving that as we have been doing in all the examples that we've done in class today. But you don't have to memorize that table at all. All right, so what if I gave you, let's see, well, that one's the one we just did, basically. Sorry, my other computer has about given up. All right, so I want you to differentiate the following power series. So we have f of x is equal to the cosine of x squared. And we want to differentiate the Taylor series about 0 for f of x. Now keep in mind the Taylor series about 0 is also known as what? It's called the Maclaurin series, right? So, don't let that part stress you out, but sometimes they'll call it 1, sometimes they'll specify. Okay, so we know from the table that they gave us that cosine x in general is equal to the summation from k equals 0 to infinity of negative 1 to the k, x to the 2k over 2k factorial. Now, if we needed to, could we show that? Well, sure, we just have to take the first few derivatives and all that good stuff. But cosine is an even function, and only even powers appear in the cosine power series. And so that would look like, let's see, when k is equal to 0, this would be 1. When k is equal to 1, this is going to be minus x squared over 2 factorial. When k is equal to 2, it's going to be plus x to the 4th over 4 factorial, and so on and so forth. When k is equal to 3, it'll be an x to the 6th over 6 factorial, then it'll be x to the 8, 8 factorial, etc. Okay, so that's what the power series for the cosine of x looks like. So the cosine of x squared would be what we get when we just replace all the x's in here with x squared. So we would have 1 minus x squared squared over 2 factorial plus x squared to the 4th over 4 factorial, and so on and so forth. So that would be 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 etc. Okay. Now, what would your power series representative look like? We could do that. I mean, just replace the x's up here with x squared. We wanted to take the derivative. So the derivative of the cosine of x squared will be the derivative of this. So if you're doing it term by term, we would have 0 minus 4x cubed over 2 factorial plus 8x to the 7th over 4 factorial minus 12x to the 11th over 6 factorial plus 16x to the 15th over 8 factorial, and so on and so forth. Okay? Is everybody okay so far? All right, the question is, how do we find a power series summation for that? How are we going to simplify it? What do we expect it to be? What do you expect the derivative of cosine of x squared to be? Well, we expect that derivative to be negative sine of x squared times 2x, right? I mean, in general, that's what the derivative of cosine of x squared is. So my expectation is that I would be able to factor out a 2x from this and come up with a formula for the sine of x squared. So I'm going to factor out a 2x. If I factor out a 2x from here, what will I have left? Well, I will have except that's a negative there. Okay, so I will have 2x factored out there. I'd be left with a 2x squared. No, 2x to the first, sorry. Over 2 factorial, because I'd have a, did I just say factor out 2x? Yeah, 2x squared times x is x cubed there. I want to factor a 2x out of here, so I would have a 4x to the 6th over 4 factorial. I want to factor out a 2x here. I would have a 6x to the 10th, right, over 6 factorial. If I factored out a 2x here, I would have an 8x to the, 14th over 8 factorial, and so on and so forth. Is everybody still okay? Do you know why I factored out that 2x? What we're trying to do is find a power series representation for the derivative of the power series that represents cosine of x squared. Since we're doing this by term-wise, I know what the derivative of cosine of x squared should look like. It should be the negative of the sine of x squared times the derivative of x squared, which is 2x. So I should have a 2x times what's left here should be a power series representation for the sine of x squared, the negative of it. So that's what we're looking for. So we have a 2x times. Anything cancel? Well, yeah. 2 cancels with 2 factorial and leaves a 1 factorial. 4 cancels with 4 factorial and leaves a 3 factorial. 5 factorial, 7 factorial. So we have negative x squared to the first over 1 factorial. This would be x squared to the third over 3 factorial. X squared to the fifth over 5 factorial. X squared to the 7th over 7 factorial. If I want it to be the negative of, I could have factored that negative sign out earlier, but we'd have negative 2x times x squared over 1 factorial minus this is just a power series representation. Let's see. We would have 2k plus 1 factorial, negative 1 to the k, times x squared to the 2k plus 1. That, using the known power series from that table that I just showed you, is a power series representation for the sine of x squared. Now, on ones like that, if I wanted you to use something from that table, I would provide that table for you. Some of the homework questions, I think, in this section, like, have the table from that page built in. Does that make sense? I mean, like, you know how back in chapter, I think it was early chapter 6, some of the integral questions, they would build in the basic integral table. They'll build in the basic power series table for these. Is that what we expected our derivative to be? Well, yeah, it is. And I used what I was expecting to find to determine how I wanted to factor things out. I knew that I should be getting sine of x squared times negative times 2x. So I went ahead and factored out a negative 2x for that part and showed that what I had remaining was a power series representation for the sine of x squared. Okay. Now, these take some manipulation, they take some practice, right? So one of the things that you'll need to do is be prepared always to write out the first few terms of the series and then take the derivative term by term if needed. Could you take the derivative from the power series representation? Sure. Let's see if I can find it. What did we have? Power series representation for the cosine of x squared would be the summation from k equals 0 to infinity of, we would just replace x with x squared in the power series for cosine. So we'd have negative 1 to the k, x squared to the 2k over 2k factorial. So that would be the summation from k equals 0 to infinity of negative 1 to the k. That would be x to the 4k over 2k factorial. So if you're taking the derivative term by term, though, on one like this, I think it's a little bit easier than doing it from this part sometimes, because here you go, okay, this would be the summation from k equals 0 to infinity, negative 1 to the k. The derivative of x to the 4k would be 4k x to the 4k minus 1 over 2k factorial. So you go, well, that kind of looks a bit weird. It can be difficult to figure out how you would do some simplification in here if you simplified this first. So on one like this, if I'm taking the derivative from the power series version, just because I get to this part and I go, I'm not really sure what to do with that necessarily to try to get back to the sine, what you can do here is, instead of simplifying it first, just take the derivative using the chain rule. X squared to the 2k would be 2k times x squared to the 2k minus 1 times 2x. See how this looks a bit easier to simplify than this one? Are y'all still hanging in there? You mean here? Okay, these parts are constant, right? So they're just hanging out. You take the derivative of x to a power, you bring the power out front, and multiply by the x to the original power minus 1. That's all I did. The problem that I was trying to get to in this part is the fact that that's not really easy to work with, yeah? Because you look at that and go, well, I'm going to need to simplify that, and looking at it this way is not easy to tell how that would simplify. So what I was trying to make the point of is, instead of simplifying this first, it's probably going to be easier to just leave it in this form and take the derivative from there. So I still have the negative 1 to the k, 2k factorial, those two parts, but the derivative of x squared to the 2k, you bring the 2k down, x squared to the 2k minus 1 times the derivative of x squared, which is 2x. So that kind of helps us with simplification, because we know that when you have 2k over 2k factorial, that cancels and leaves a 2k minus 1 factorial. And so now we have a negative 1 to the k x squared to the 2k minus 1 over 2k minus 1 factorial times a 2x. And so this time, you know, if we look at the first couple terms, we'll notice that it's shifted, but this part, 2k minus 1 or 2k plus 1, they're both always odd, right? You know, if k is an integer, 2k is always even, and 2k plus 1 or 2k minus 1 is always odd. And so this guy would start at k equals 1 to infinity. Yeah, in this form. Because if we didn't, we'd have a negative number down there. We can shift it, if you like, back to 0, but I think it may be a little bit easier to see that you have a 2x times a power series representation for sine this way than it would have been if we had continued with this one. But don't be afraid, because, you know, even though it's kind of a painful process, where'd it go? Even though it's kind of a painful process to take the derivative term by term, it works. And I think a lot of times, as far as knowing where it starts, you know, where you should start with your k's and all that good stuff, it may actually be easier to go through the kind of brute force process of taking the derivative term by term from the written out series than it does going back to the condensed version, so to speak. Whew, that's a lot in one day. So, couple things. You have one assignment from 11.3 and 11.4 combined. That's due, well, it's supposed to be due Wednesday, but obviously, you know, I won't be here. Make sure you send me emails. Would anybody be interested in like a Zoom on Sunday evening? Okay, so would 8 be too late? Okay, I'm sorry. I know that's kind of late, but okay, so I will plan. I know we won't be here for review on Wednesday, but you do have the review problems in your homework, okay? And so just work on that not departmental review, but exam 3 review that's in homework. Do the homework from 11.4 and 11.5, and then no class on Wednesday, but we will Zoom Sunday night, if you can, at 8 p.m. And we'll just do that in our class Zoom, so in this same normal Zoom for us, okay? If you can't, I will make it where you can. You should be able to see them, but I don't remember if they're available right at this moment or not. But I'll make it where you can look at them. Yes, yep. So I'll set those. All right. Any other questions? Okay, we are, golly, to our last chapter of Calculus 2. Yeah, and chapter 12 is pretty much completely different from everything we've done up to this point. So, yeah. But it is also information that's really, really important for you going into Calculus 3. So, all right. But you guys have a great rest of your week. I will talk to you if you can make it on Sunday. If you can't make it on Sunday, I totally understand. But remember, your exam is Monday at noon. Okay, so you won't come to Zoom on Monday. You'll just go straight to taking your exam. All right. Let me know. Okay, let me know if you have questions.